array is almost sorted. Yeah. So many times when you read the question, some critical word, very important. Here, almost sorted. This word important. So here we are talking about one special property of insertion sort. After you learn the insertion sort, you need to know this property. Okay? Yeah. All right. Not many properties, yeah. So this one is important. Which of the following algorithm is the most efficient to sort this array? Answer insertion sort. Why? The reason is very simple. Why? I hope when you answer this, you know, because almost sorted, this property, that means most of the elements are in order, but there are only a few places. There are some clusters, you know, scattered locations, clusters. That part unordered. So you only need to fix that part, but you don't know where are those unordered clusters. You don't know. So you need to run the whole algorithm from beginning to end. Okay? All right. But we know, so here, when we do analysis, we just use the array, ordered array. So here, we assume we have an input. Input is ordered array. We throw in an ordered array into our program. Okay? Selection sort, even ordered, you still need n squared. You still need n squared. Because you need to do all the possible comparisons. Okay? Insertion sort, ordered array, big theta of n. Merge sort, ordered array, the best case, even the best case, n log n. Still n log n. Okay? I didn't derive it in class. Yeah. But it's still, because here you can think in this way. Merge sort. Because we always split in the middle. Okay? We always split in the middle. That means the data distribution is very balanced. For very balanced data distribution, the best of case, worst case, the difference is very small. There is some difference, but difference is quite small. Okay? Yeah. So in the same category, the best case, worst case in the same category. Same category. Because data distribution, evenly distributed. A quick sort, ascending order, yeah, this is very special. Quick sort, ascending order, we would get the worst case. And it's where? Worst case. Okay? Yeah. So now you can see insertion sort, the best. All right. Question number.
Wait. N squared, that's worst case or average case?
Worst case. Average case, n log n.
Okay.
And, you use your logic understanding, n log n, because average case, we know it's better than most of the other sorts. Average case. Better than. How can it be n squared? Okay? How can it be n squared? It's better than most of the other sorts, the average case. So, because that's the, we say, overall efficiency, the best. The best among the known sorts, among the known sorts, general purpose known sorts, not special purpose, general purpose known sorts. Okay? All right.
Wait, I'm sorry.
Yeah.
What was it about? You're saying that about quicksort?
Quicksort, I say, it has the best overall efficiency. Best overall efficiency among the, yeah. Sometimes I may say something related to homework assignment. Yeah. So I mean give you the answer. Yeah. Whatever it is, all right? Whatever it is. Actually, in notes, I said that in notes. Yeah. In notes, yeah. Because when I teach quicksort, I have to tell you this. This is the best property. After you learn a quicksort, you need to know this property. Okay? After you learn insertion sort, you need to know this property. Okay? Right. After you learn the merge sort, you need to know it has the best worst case efficiency. Merge sort. Yeah. Probably it's also, yeah, I don't know. I couldn't remember what I gave you in the homework assignments. So when I say something, I just, whatever it is. All right. Okay, let me erase this. Suppose, number 2, that we have an ordered array and we want to do the binary search on this one. 6 comparison. The answer is no, we cannot. Okay? Average case. Average case, you cannot just use our, this average, when you do not have the specific weights. So this average, we do this, because 50%. Best case, you assign the weight 50%. That's 1/2. Worst case, you assign the weight 50%, another 1/2. Weighted average. But for our binary search, it's not that case. Best case, worst case, not 50%. The best case, worst case, or we say closer to the worst case, more weight. Look at our binary search, binary tree. Okay? Pretty much like a triangle like this. This is the best case, right? Best case, the percentage is extremely small, tiny, okay? Extremely small. Now, let me use 0.1%. Okay? The worst case, close to worst case, this part, the weight, so big, okay? So we can probably, put a 95%, for example, right? Just some rough estimate, okay? Rough estimate. So you can see, when we do weighted average, the average should be very close to the worst case, because the weight is so big. Push the weight very close to average, very close to the worst case. So it's not that here, because you use this formula, then it's 50%. That's not right. Okay? Yeah. All right. Number 3, after we apply each partition step in the quicksort, we can guarantee that at least one element is in place. True, because the special element pivot. We guarantee the pivot must be in place. Although it could be more than that, right? Yeah. So other elements we don't know, at least more than that. More than that. But if we do our understanding a little deeper, yeah. So here, let me draw the diagram a little bit. Suppose this is original array. Okay. Yeah. All right. After the partition, the pivot, we put it in place. Okay. In place. Then we have left subarray, A subarray, and right subarray, B subarray. Okay, all right. So first we can guarantee this element in place. Other than this one, all the other elements we cannot guarantee in place. But there is a possibility in place, not in place. All right. For example, if some element here happens to be in place, there is a possibility, right? Happened to be in place. Okay? Actually, it does not help much. If it's in place, it does not mean we can benefit from the element in place here. Why? Because when we do divide and conquer, when we do recursion here, when we apply another partition step, we may change its position. It will be not in place. There is a good chance it won't be in place after another round partition. So that means for other elements, even if they are in place, it doesn't help. Because we will move those elements to some other locations in our later process. It doesn't help. All right, yeah. So that's something. All right, number 4. When we do the partition step in the quicksort, is it a good idea to use media? I remember Harris answered this question, right? Yeah, once. Yeah, I still remember answer, not a good idea. It's a bad idea. Yeah. The reason is finding the median too costly. Not worth it. Okay? Not worth. Too expensive. Too expensive. Not worth it. Okay? Yeah. Actually, if you do it this way, you will significantly slow down the sorting. Greatly slow down the sorting. All right, so
You might not have time for this. You know what the big O? You know what the big O of finding the median is? The efficiency.
yeah, linear. Yeah. That big O, this one, but that coefficient is quite big. Okay? Constant coefficient of approximately 16 times that high. So not worth it. Not worth it. Our partition is n. Okay? 6 times slower. Okay? Usual partition n. But that median 16 times n. Too much slower. Alright? Number 5, when we use the divide and conquer view to understand merge sort, which of the following steps is trivial? Trivial, not much work to do. Yep. Minimum amount of work. Divide step. Because we split right in the middle. right in the middle. Not much to do. Just do one division operation. First index plus last index divided by 2. Only do that operation. That gives us the split point. Splitting 2 arrays, 2 subarrays. That's all we need to do. So we say trigger. Okay? Alright. Number 6. When we use the divide and conquer view, understand quicksort. Which of step is trigger? Combine. Combine. Yeah. So here I hope, because sometimes some students may feel, how can we memorize so many properties, right? Yeah. It's hard, so many properties. When you understand, then it is not hard to memorize. So you need to follow the logic. Follow the logic. Yeah. When we study the quicksort, we spend a lot of time on how do we split given array. We spend a lot of time. Yeah. If you follow the story, not the same here, sorry. Yeah. All right, so P here, A, we have the property. B, we have the property. All right? So then when you combine, just put them together. Do nothing. All right? So we say combined step is trigger. Okay. Without understanding, without logic-based understanding, try to memorize these properties. That's hard. That's hard. Okay? Yeah. You need to memorize things literally, right? Yeah. That's hard. Number 7. Which of the following sorting algorithms has the property that its worst case efficiency is in n by n? Very obvious. I mentioned before, merge sort. When we design a merge sort, we want to make its worst case more efficient. No. Worst case, the best we can. Here you can see I all check your understanding the basics. Okay? If you're familiar with the materials. Not very deep. Okay? I didn't check you deep understanding. Alright? Yeah. Number 8. When we apply the quicksort on a given array, is it possible that there exists an input such that no swap operation is needed to get the whole array order? It's possible. No swap operation, whole array order. What is that special input? Anyone can get a sense. Yeah. No swap. Do all the partitions, but you do not need to do. That means you do not need to change the location of the pivot. It is always in place. The pivot is always in place. Ordered array. Yeah. Ordered array. The pivot is the last element. Okay? Last element. In place. In place. Yeah. Yeah. After you split, whatever you do, but the split only reduce every time reduced by one element. The next pivot also in place. also in place all the time. So no swap needed. Okay, that's simple property. Yes. Okay. But you need to know which one. Okay, not guess. Some of you may answer questions like this, probably, make a guess. Or by your, maybe a little better than guess, based on your impression, intuition. Many times based on your intuition. Yeah. Number 9, if an array is too big to be loaded into the main memory of your computer, is it possible that one can design some special algorithm to get this array sorted in the same computer? I describe a story when I talk about merge sort, split. That huge array, we cannot load it into the main memory. Can we split it into smaller subarrays? Each time we only load a smaller subarray, get it sorted. Then output, write it to the hard drive, load another subarray into the main memory, sort it, output in the hard drive, and so on. Okay? Get all subarrays sorted, and write them on the hard disk. But not sorted, right? So that's the first round processing. Still, the whole array not sorted. Then we do merge operation. Merge two adjacent subarrays. Every time, two adjacent subarrays. But when you merge two adjacent subarrays, when the subarrays grow larger and larger, sooner or later, you may not be able to load the whole subarray into the main memory, right? You may not be able to load the whole subarray into the main memory. So don't worry, load portion of it. Then write sorted, merged array to the output. Portion by portion, So you can get whole array sorted. Just load portion of the data in, write it out, portion in, out, in that way. But you need to control, organize the loading, process in a well-organized way, so that you won't mess up. So you get the whole thing done. Okay? So it can be done. Okay? Yeah. It takes a lot of effort, but it can be done. All right. Question number 10. Which of the following sorting algorithm is not an in-place algorithm? Here, do not confuse this in-place with our previous meeting in place regarding the elements in place in an array. Here is in-place algorithm. In-place means, let's review in-place, the meaning of it. The extra space used for this algorithm, big theta or big O, big theta of 1. Okay? Oh, it's better big O. How about that? Here we use big O of 1, probably better than big theta of 1, right? Because big O of 1 we include 0, right? We do not use any extra space, although it's there. Yeah, because we have to use some index, right? Yeah. It's rare. We do not use any extra space. Yeah. But it, at least, by its meaning, it includes the 0x extra space case. Big theta 1, it does not include 0. Okay? Because big theta, you have lower bound, right? Non-zero lower bound. So it does not include 0. Big O, it includes 0. So that's the main difference. All right. So that's the in-place algorithm. All right. It's not in place. That means most of them in place. Only one not in place. Here you can assume, if I do not say anything, when I give you 4 options, multiple options, if I do not say anything, by default, only one correct answer. Okay? Only one correct answer. But if more than one, it's rare. If more than one correct answers, I will write something to let you know. Choose all that can apply. Okay? I will put a parenthesis. Choose all the options that can apply. If I do not write that, you'll assume only one correct answer. Okay? Yeah. All right. Yeah. But sometimes, there is a situation like this. Sometimes, so one student may feel both look correct, look or partially correct, some partial, somewhat correct, but 2 options look somewhat correct. In that situation, choose the one you feel the best. You have 2, so which one is a little better? Take that one. A little better. Okay? All right. So that's quiz number 4. Next, quiz number 5. Which of the following sorting algorithm is? Oh, the same question?
Yep.
All right. Yeah, I got confused. Yeah. Sometimes I check my questions, my own questions. Yeah. But sometimes anyway, don't worry. Yeah. So not in place. Yeah. Here, but I can use this chance to explain. Okay. All right. If I put a quick sort here, we still treat not in place. Okay? Yeah. So there is a quick sort. So I use this chance to review the quick sort. Yeah. Because for the quick sort, we know its partition step is in place. No problem. Its partition step is in place. But the whole algorithm is not in place. Is not in place. Due to recursion. Okay. Recursion, we need to maintain a deep stack, right? Yeah. Sometimes the stack could be very deep. Then you cannot say the extra space used bounded by big O of 1, right? Yeah. Too much space used. So you cannot say it's in place. In place, we won't have that kind of thing. Okay? So you can have this. Usually, if an algorithm is implemented in recursion, we cannot treat it as in place. Okay? So we have to make it iterative. In order to get an in-place sector, we have to make it iterative. Or, remember, or we use some other methods to, avoid deep stack. So that may not be easy. So in general, so we say recursive algorithms, we don't treat them as in-place algorithms. Okay, all right. Yeah. Sorry, I covered it. In order to store a binary tree structure in an array, binary tree in a heap, specifying the parent-child relationship, we have to use linked list. No, false, right? Binary. So our heap, for example, we do not use linked list data structure. So you need to have specific example in your mind. After you learn the heap, you can do it without linked list. Number 3, can we use the location in an array with index 0 for a node? 0 for a node in a heap data structure? No, right? Because the parent-child formula, it violates the parent-child formula, relationship. All right. The simple property. Number 4, for which of the following sorting algorithm, the worst case efficiency is much worse than the average case efficiency. But here we use the asymptotic notation to see that. If in the same asymptotic notation, although there is a difference, but we treat in the same class. Okay? If they are in 2 different classes of asymptotic notations, then we treat them, the difference is larger. Okay? Because 2 different classes. Okay. All right. So here we compare average case and worst case. Insertion, both in the big theta of n squared. Okay? Worst case, average case. Average case, just constant 1/2 times that worst case. Merge sort, average case, worst case, both in n log n. N log n. Okay, quick sort, average, worst, average, n log n, worst, n squared. Okay. Heap sort. Remember, we make worst case in n log n. When we do the design, we have 3 requirements. One of them is this. So both. So heap, both. In okay. So you may ask, how about the best case? So best case, worst case, average, all in this category. Heap, actually, for this part, very similar to the merge sort. Because after we make it that heap structure, what's the heap structure? Near complete binary tree. Complete boundary tree, that's the most balanced boundary tree. Near complete, that's a near balanced boundary tree. That means the data distribution is in a very balanced way, or quite balanced way. That means similar to the property of the merge sort. Even split, data distribution is very balanced. Here, the data distribution is near balanced. So here you can see similar property regarding the efficiency, all in this category. So there your answer is crystal, because they are in two different categories. All the other three, they are in the same category. Three options, they are in the same category. All right. So you need to be familiar with, all these things. So after you learn, we have learned so many sorts. So at least when you do comparisons like this, so you know all the details. All right, yeah. All right. Question 5, given a node in a heap, if we know that this node does not have any right child, all right, yeah. Can we say that this node must be a leaf? No, left child, right? It could have a left child without right child. Okay, so there is a possibility. Okay, all right. All right. So the question, so here answer, no. All right. But if I modify this question slightly, then I ask you the same question. So given a node in a heap with n nodes, where n is odd number, not even number, odd number. Okay? Yeah. Then we ask the same question. If we know that, so the heap has this property, okay? Heap has this property. Then we consider a node in this heap that does not have any right child node. Can we say that this node must be a leaf? Odd, the heap has odd number of elements, nodes. This heap, not even odd. And the one node does not have any right child. Can we say it must be a leaf? Yes, right? Yeah. Yes. Odd. Answer is yes. Odd then, because if we have odd number of nodes in a heap, then any internal node must have both left child node and the right child node. Left, right, both. Okay? Internal node. All right. Number 6. Given a heap with even number of nodes, which of the following statements is correct? Do not count the array element at index 0. First option, the number of internal nodes equals the number of leaves. Second, the number of internal nodes is greater than the number of leaves. Third, the number of internal nodes is less than the number of leaves. First option. even, so we can split right in the middle. Okay? But if you answer the question, we have the original formula, right? Remember, original formula, number of leaves. This is number of leaves. Number of internal. Okay? When n is even, the same. Ceiling function, floor function, we get the same thing. But for R, different. For R, it's different. Even the same. Okay? Just some simple properties of B. All right. Number 7, is it possible that one can sort 5-element array in 7 comparisons? Yes, right? I did it. I did it. But before I did it, remember this quiz actually I gave you before I made that video. But in a notes before, yeah. So remember, so when I talk about notes, finding the median selection, module 4, when I talk about what topic? When I talk about selection problem, finding the median. So I wrote, so 2 important problems. I give you the answer. First one, find 5-element array. We can use 6 comparisons. Sort 5-element array, we need to use 7 comparisons. I wrote those 2 results on that notes. Okay? So that's before. In module 4, I did that. So if you are familiar with the notes, you can find it. Okay. Yeah. So then I give you this question. I want to check if you still remember that important result. Then later, I make a video, in Thanksgiving break. Video, not Thanksgiving break. The class right before the Thanksgiving break. So we, whatever. Actually, no, before that. Anyway, so problem solving session. I solved it. All right. Number 8. Does there exist a search algorithm that can complete a search operation with the average case efficiency bigger of 1 without using much more memory resource than necessary? Yes. Action. Without using much more memory resource than necessary. Here we're talking about that index search. Index search will use a lot of memory resource for hashing because we make our hash table just enough. So we may leave some room. Okay. All right. So here, remember, and the number of elements to be stored in a hash table and the number of slots in the hash table. All right, yeah. We know we we should make n greater or equal to n. Okay? Yeah. So we don't want to use linked list here. Linked list, even if n less than n, we can still do it. But we try to avoid linked list, the complexity of that. Yeah. All right. So the minimum requirement n less than or equal to n. Yeah. But here, when you use it, you would like to make n less than n. You leave some room in your hash tables. You make, slightly more slot number than the number of elements. The reason you leave some room, you want to reduce the collision problem. Collision problem. Okay. That will slow down the performance. But we know the storage is very cheap, right? We just increase, not too many, just reasonable, more number of slots. And we want to reduce the collision significantly. Then it's worth it. Worth it. All right. Number 9. Is it possible that one can solve the element uniqueness problem with the average case efficiency in big O of 1? Yes.
Big O of 1 or n?
Sorry, it's big O of n. Yeah, cannot be big O of 1. Yeah. Big O of n. Yes. By hashing. Okay? Hashing. So, when you go to interview, if they happen to give you this question, using the hashing way, that would be your best answer. Okay? Sorting way, second best. Sorting way, second best. Without sorting, just do comparison in the brute force way, that's the worst. That means you will lose the job. Okay? The third one, you will lose the job. Second best, you still have a chance. Second best. Hashing, increase your chance to get a job. Okay? Just something like that. This is an interview question. Okay? Yeah. All right. Number 10. Does there exist a perfect hash function that will result in any collision that will not result in any collision for it? No. No perfect hash function. You only want to control the collision rate as small as possible. But you cannot make it 0. Okay? The collision rate can never be 0. All right, so that's the quiz number 5. Then, the last thing we need to do, we do not have much time, less than 10 seconds. Let me do just so this first heap question. Given a max heap with this many nodes, whose position number correspond to 1 through 536. Now we want to consider a node with position number 135. What is the height of this node? So this time we go the opposite way. We don't know its height. We know its location, but we don't know its height. For many students, I gave this question before, many students, when they did the calculation, they did the wrong direction. So why it's wrong? So here, I tell you the typical problem, so you can avoid that. So we know the heap, the structure, binary tree like this. Okay, yeah, many levels, large number of students. They count the height. They come from root. Okay, yeah. They come from root. They count like this. Okay, yeah. So now your 135 is somewhere here. So they count the height, they counted the, this number of levels. That's wrong. We know we come from bottom. Okay? We do not come from top. We come from the bottom. Right? Yeah. But here, we do this way. We apply our formula. So here I show you for this question, we apply our formula. Location from 1 through 536. Okay, all right. So, all nodes. Then, we look at the level, leaf level. Leaf. All these leaves block. So we want to know this location. Okay? So this location, flow function plus 1, right? Plus 1. Okay? Yeah. So what's that? 268, right? Right? Yeah, 268 plus 1 equals 269. Okay? All right. Yeah, so that's the leaves. Height 1. Height 1. So this position is 268. Then that position is over 4 plus 1. Okay? Yeah? Based on our formula, plus 4 over 1, right? So let's calculate it. 1, 3, 4 plus 1, right? Yeah. That equals 135. This is the height 1. Height 1 node. Okay? Height 1 node. Now, yeah, 135. Remember? Yeah, 135. Just this, say the lower bound. This is 135. It's inside height 1 range. Height 1, that's inclusive. So when we write these two numbers, that's inclusive. Include both ends for height 1. Okay? Yeah. So when you do the question, you just do a few calculations using the height range formula, lower bound, upper bound, calculate a few of them. Which interval covers the index, the given index? In this way, you can find the correct answer. Now those students, from top. Okay. Glean from top. That's wrong. That's wrong. Okay? All right. Last question. You'll still have a few seconds. Last question. 4 seconds. 4. Last one. Last one. Draw a max heat. Max heat. Max heat. Draw some levels. All right, yeah. Just enough many levels. Oh. This is the last level. Okay. Last one. All right. Another. All right. Here. Let me control the time. We want to find the location of the minimum. Smallest index for the minimum. Smallest location. All right. minimum. Alright, yeah. Alright. So we want to push this location as early as possible. Okay? Yeah. Is it possible for this last location? Yes, it's possible, but not smallest, right? Is it possible here? We put a minimum here, still follows the max key property. Yes, it's possible. All right, yeah. So we just keep pushing up. Okay. Yeah. Is it possible to put it here? Put it here. Yeah. Because it is a leaf. It is a leaf. It has no child. That means it does not have to be greater than any element, right? So this is still a valid location for the minimum. So we can push earlier. But if we push one more location earlier, we go here, then it has a child, it cannot be minimum, right? Yeah. So the earliest location, smallest location we can push is this one. Okay? Yeah. So in the leaf range, yeah, so this is in the leaf range. Yeah. The earliest place you can push. Okay? Smallest. All right. How about second smallest? Third smallest? Just think about it. Second smallest, you can make it greater than the smallest. Only greater than the smallest. Third, you can make it greater than 2. Smallest, second smallest. Okay? All right, think about it. Think about it. All right, let me finish right here. I hope when you use this diagram, you can figure out how to use formula to represent location of the smallest element. Yeah. Leaf, what is the lower bound of the leaf, right? Lower bound. Yeah. Smallest location for minimum, that's the lower bound. Yeah. Lagging. Lower, yeah, lagging, very bad. Lower bound for the leaf range. Leaf range. Okay. Yeah. If you know the lower bound for the leaf range, you have the answer. Okay? You have the answer. Very easy. Very easy. We did several times. We did several times. All right. Yeah, that's it.